Hello student, welcome to the lecture. In continuation with previous lecture, in this lecture we are going to discuss the isomerism in square planar complexes. So as we know that in tetrahedral complexes, it is not possible the cis and trans isomerism, means the geometrical isomerism is not possible in tetrahedral complexes due to the ligand position is equivalent, but the optical isomerism is possible in tetrahedral complexes. Now, in continuation with this previous lecture, we are going to discuss the isomerism in square planar complexes. So first we are going to discuss isomerism in square planar complexes. So in that type we are going to discuss that is Ma2B2, where A and B are the ligands. Means that here if we draw the diagram of that is AABB. So the structure of this complex is square planar, where AA are on the same side, BB are on the opposite side. So here this is a cis isomerism, and here that is a trans isomerism here. So this type of isomerism is possible in this geometrical isomerism is possible in square planar complexes. And the example of that isomerism is diamine dichloroplatinum complex here. So this is the example of that type. The second type that is and that is, and the example of that isomerism is same one, that is platinum diamine platinum chloride. So if you draw the structure for that, then it will look like as this. This is a cis position because NH3 is on the same side. This is a cis position because NH3 is on the same side. So here this ammonia is on the opposite side, so this is a trans one. So this is a type that is Ma2B2 is a cis and trans isomerism of geometrical isomerism of that type. So now the next one, that is ABCD of that isomer is a platinum, pyridine, chlorine and bromine. Here there is a 4 types of ligand is there, that is A, B, C, D. So here if we draw that isomers, that is pyridine. that is here, here that is chlorine, that is so that is 1, 2 and 3 possible isomers are possible for this Ma. M that is the center of metal atom, A, B, C, D means that is the 4 types of ligand, and here if you fix the position of ammonia here and then we have to rotate this 3 ligand along this axis, then it will be show or it will be give the 3 isomers. It will give the 3 isomers. So this is a isomer of this type. Now let's discuss the isomerism, stereoisomerism in coordination number 6. So here we are going to discuss the stereoisomerism in coordination number 6. As we know that there is an octahedral geometry for coordination number 6. There are various possible arrangements in coordination number 6. Let's discuss one by one. First, we are going to discuss that is Ma4B2. And the example of that so here if you observe that is cis1 that is trans. So here for that type there will be the 3 possible arrangement. Only 2 geometrical isomerism are possible, that is cis and trans. Optical isomerism it does not show by this type because there will be the adjacent position of the equivalent or adjacent position of ligand, so that's why it does not show the optical isomerism. So just 2 geometrical isomerism is possible is in that type. So here that is the 3. So here that is a 5 possible isomers for this AB2B2C2 type. So here 1, 2, 3, 4 and 5. Among that the 5 number isomer have a optical isomerism. This shows a mirror image, superimposable mirror image of each other. So with the optical isomerism, so here the 5th isomer shows the optical isomerism. This is non-superimposable mirror. If we pass the plane or if we see the mirror image of that, this will be the isomers. So these 2 are shows the optical isomer. So here in that type, that is Ma2B2C2, there will be the 5 geometrical isomerism and 1 that is a optical isomerism is possible in that Ma2B2C2. So now let's discuss the next type. So this is a geometrical and this is an optical isomerism which is possible in this Ma2B2C2. So now let's discuss the next one. The third one, that is Ma3B3. That example is so here, that is, if we draw the structure of that, that is NH3, 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 that is Cl, Cl, Cl. So here, if we draw that type, again, it is Cl, Cl, NH3, 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 Cl. So this is this NH3 or shift. So it is a trans, because this Cl was on the opposite side. So here, this is a two possible isomerism possible is in this Ma3B3. There will be no any optical isomerism because the ligand positions are equivalent to each other. So that's why it is not possible optical isomerism in this type. So let's discuss the next one. This is the fourth type, and the example of that is M is a central metal atom, and there will be the 6 different ligands attached to the central metal atom, that is A, B, C, D, E, F type. This, for example, we take an example, that is NH3, pyridine, ammonia, chlorine, NO2, Br, and iodine. So there will be the 6 different ligands, 1, 2, 3, 4, 5, 6. So 6 different ligand is here. If we draw the structure of that, NO2, that is NH3. So if you see the structure of that, it will be just giving only one isomer. If you observe this complex, there will be the 30 isomers are possible for this type of arrangement, and out of 30 there will be the 15 isomers shows optically active compounds. So this is the type of where the metal are coordinated with 6 different ligands. So now let's discuss the next one. Next one, that is 5th number, that is MMA2B2. This A2 is a bidentate ligand. Looks like as like. That is ethylene diamine ligand. This is ethylene diamine ligand, that is chlorine. Here that is chlorine. This ethylene diamine is on the same side, so this is cis. This cis isomer show the optical isomerism, that is so these are the two mirror images of, and thus there will be the one more isomer is possible, cis and trans. So this is a trans one. So in this isomerism there will be 3 isomers. In between these 3, the cis shows the optical isomerism, and there will be the trans isomer is here, sorry. Trans isomer is here. So this is the cis isomer. We show the optical isomers of each other. This is superimposable mirror images of each other, and this will be the trans isomer of that type. Now let's discuss the next one. Now that is a 6 number, that is Ma2B2 and C2. Means that there will be only one bidentate ligand, and this is the another ligand which is monodentate, and means there will be the 3 different ligand. One is a bidentate, this is another ligand, and this is also another ligand, that is B and C. So let's discuss the example of that complex. So if we again taken that type, that is ethylene diamine, pyridine and chlorine. Here there again 3 isomer is possible for that arrangement. Here cis isomer are superimposable mirror of each other. See they show optical isomerism, whereas this is a trans isomer, so this is a cis trans, and on another that the cis shows the superimposable mirror image of each other. So this is a 3 possible isomers for that type. Now let's discuss the next one. Next one, that is example of that type, that is so this is a cis and this is a trans positions of each other. So in this type there will be the 2 isomers, this is cis and trans. So these 2 isomers show, so in this type, that is MAB3 3 times. So here this shows the 2 isomers, cis and trans. Now let's discuss the next one. That is 8th and last one, that is again that is bidentate ligand here. So if we take an example as that is tetra is ethylene diamine cobalt complex. So here if we draw that type, that is ethylene diamine. Here again that is ethylene diamine. Type does not show any geometrical isomerism, because the sides are not distinguishing between cis and trans. But optical isomerism is possible. This is all about the cobalt tetrachloroethylene diamine here. So there will be only 2 optical isomerism possible, which are mirror image of each other, and there will be no any geometrical isomerism possible in that type, because the cis and trans cannot distinguish it, because this is a totally bidentate ligand and we cannot distinguish the position cis and trans. So this is all about the stereoisomerism in coordination number 6. Now we will stop here. In next lecture we are going to discuss the Pauling valence bond theory. Thank you.